Welcome, welcome, welcome to the final piece of our three-part series concerning linear regression. In this video, we'll talk about how to do linear regression in an online fashion. So let's dive right in. The notation for this set of slides is the same as the previous ones, but if for some reason, like, I don't know, you tip back a few too many beers between this lecture and the last one, well, check out the description by following this link. So what is online learning or online processing? And why do we need it? We're living in the time of big data. We have data sets that are gigabytes, terabytes, petabytes, and they're only getting larger. We cannot obviously just load the whole data set into computer memory and perform our calculations all at once. In the case of live streaming data, we would quickly fall behind if we had to run all of the previous data points with every single new data point that we wanted to classify that came in. This problem is very visible if you're trying to do deep neural networks on a GPU. There just isn't enough space for the structure of the network and for all the data to reside in GPU memory. In the first lecture, we discussed frequentist approaches to linear regression. And in the second video, we discussed a Bayesian viewpoint. In this lecture, we will compare and contrast the frequentist and Bayesian viewpoints as they encounter online learning. Let's start with the frequentist approach that we learned in the first video of the series. One method of doing online learning from this viewpoint is a method known as least mean squares. This method uses stochastic gradient descent to solve its sequential problems. But the details of that specific optimization algorithm will be covered in much more depth in later neural network lectures. But for brevity, we'll discuss it briefly here. So we know that the error function can be rewritten as a sum of the error of the data points. This doesn't mean that we have to process the data points one by one. We could have groups of 10 points, for example. What this algorithm does is start with a vector W that is initialized to some starting value. This would be our W sub 0 parameter that you should remember from our previous lectures. At each new iteration, in this case, each iteration will be at each new data point, but as I said, it can be a set of data points as well. So at each new iteration, we update the values of the vector W with eta, our learning rate, times the negative derivative of the error of our data point. Eta is called the learning rate. It lets us control the speed at which our algorithm tries to find a minimum. But why are we using the gradient of the error for our data point? Well, if you remember back to the calculus training that you had in this class, and I would assume previously, you might remember that if a multivariate function is defined and differentiable at a specific point, then the direction in which that function decreases fastest will be the direction of the negative gradient. Although this is a simple first-order model, it works very well. But remember, we have to tune the learning parameter in order to get our algorithm to converge. And as I mentioned before, all of this will be covered in much more depth in the later neural network lectures. Well, least mean squares seemed nice and all, but what if you don't want to have to go through multiple passes of your data? Well, you're just in luck. There is an algorithm called recursive least squares that lets you do just that. I'm not going to go through the details of this algorithm, and you won't need to know the details of this for this class, as it would require a bit of background on Kalman filters, and that's just a little too advanced for this talk. It's included here so that you know that other algorithms with computational advantages do exist. Just a warning, there are a ton of algorithms out there, And if you find yourself interested in learning more, please feel free to dig deeper into this area. It's truly interesting to see the relationships between algorithms, at least in my opinion. So this algorithm helps you to find the optimal learning rate for your gradient descent at each step. If you look at the top equation, you can see that we have the same form as we had before in gradient descent, where r tau plus 1 is the learning rate, and x tau plus 1 times z tau plus 1 minus x tau plus 1 transpose is the gradient of the least squares algorithm. If you don't believe me, feel free to double check me. So by defining r tau as the outer product of the design matrix, we have our update step in the form of r tau plus 1 inverse. The derivation of this is actually pretty straightforward. If you want a step-by-step guide through the derivation, the Wikipedia page on recursive least squares is actually really nice. Another little anecdote about this algorithm is that it was originally developed by Gauss in 1821, but it just laid unused until the 1950s when it was rediscovered. As I said before, this algorithm is closely related to Kalman filters. Essentially, it's just missing a few of the parts of the equation. Okay, that's enough. Moving onwards. Okay, so we've covered the frequentist approach. Can we do the same thing from a Bayesian approach? Does Bayes' rule help us to formulate this problem in a way that allows sequential updates of our model? Take a moment to answer this question. How would you do it? I'll wait. Okay, if you remember back to the last video, we can introduce a prior distribution like a Gaussian. Since typically we don't know much about the distribution that we're attempting to model, a Gaussian prior is a pretty reasonable example. In this case, let's assume it's an isotropic Gaussian, like we did in the examples of the last lecture. This gives us a closed form for the posterior that we've seen before. If you remember back to last lecture, we can calculate the values of the posterior pretty nicely as shown by equations 5 and 6. That's interesting. We have an equation for the posterior that's easy to calculate and is in the form of a Gaussian. If you didn't have an idea how to do sequential updating using a Bayesian formulation, do you have any ideas now? Seriously, pause the video for a few moments. Try to think through how you would do this. I'll wait. Voila! Our posterior from step n becomes the prior for step n plus 1. Were you able to guess that? If so, nice job. If not, hey, no worries, you'll get it next time. So on the first iteration, we get the posterior from using Bayes' rule on the likelihood multiplied by the prior. For every subsequent iteration, we use the previous iteration's posterior along with the likelihood to give us the new posterior. You should remember this trick from the coin flip analogy used in the parameter inference videos. So how does this look with Gaussian likelihood and Gaussian priors? Well, you can see that the posterior is in the form of a Gaussian. As we would expect, the mean of this Gaussian is a product of the means of Gaussians that represent the uncertainty of each data point with the basis function. And remember, the basis function could just be the identity function. The variance parameter, sigma squared, is actually pretty cool. The first part of the equation, 1 over beta, is the noise that the data points themselves have, and the second term reflects the uncertainty associated with the parameters of W. Since the noise on the data is modeled as a Gaussian, and we modeled the weights W as Gaussian, all of the variances are additive. But what does that mean for how the distribution forms over time? Well, as additional points are observed, the posterior becomes narrower and narrower. As the number of points approaches infinity, the second term completely disappears, and the entire variance comes from the noise on the data points alone, or the first term in the equation. Let's look at an example to wrap our heads around that. So look at the upper left image. The green line is the true generating distribution, and the single blue point is our first data point. The pink is the variance of the functions that could fit that point. That means we could have functions like this, or like this. The red line happens to be the mean of all of those functions for the pink space. If we look to the image next to it, we now have 4 points. We can see how much the variance has been even more constrained, but there's still quite a bit of variation here. Those are still all of the functions that could fit those 4 data points. If we look at this image here, we get a better interpretation or a better feeling for different types of functions that could fit through those points. And as you probably remember from the first video lecture, lots of polynomials could fit those 4 points. If we look to the right, now we have an image that has lots of data points. You'll notice that the posterior has been severely narrowed, and that the mean of the posterior actually gives a decent approximation to the real underlying function. Let's look at one more example. So we have a true function that is depicted by z, and it has a noise term in it that we're going to represent with a Gaussian noise. We're going to try to approximate this distribution using Bayes' rule and a likelihood function that is a simple basis function of x, namely a normal line where w sub 0 is our intercept and w sub 1 is our slope. So what does this look like? So luckily I have this nice little chart here. So what we have here is the green line is our true function that we're trying to approximate. You can also see that since we don't have any data points, our likelihood doesn't exist, and we only have an isotropic Gaussian prior. Now when we add a data point, we see how quickly the posterior changes as it takes into account the likelihood and the prior as we add new points. You can see that the posterior keeps shrinking as we add points. The white cross that you see is the true parameter values, and the red lines that appear are the samples taken from that distribution. You'll notice how they pass close to the points I've created. And when there's lots of points, you can see how confident the posterior becomes. You can see after adding all of those points, the posterior shrinks considerably. And if we can add a few more points without things dying on us, you can see it keeps continually shrinking. Now what's interesting is that this is also a good example to show how much outliers can really affect your data, especially when you're doing a line fit like this. We've only had 4 points, 5, 6 points out of, I don't know how many are there, maybe 20 or 25. And now you can see over here in the posterior density how far we've gone from the actual answer. This slide here, I'm not going to speak over because it's just a summary of the demo that we just did on the previous slide. But it will be included in the slide deck of the lecture slides so that you can review this in your own time. So that wraps up our 3-part series covering linear regression. I hope you learned a lot, and as I said at the beginning of this series, linear regression is a workhorse of machine learning. But not only that, if you don't understand why and how these methods work, you're going to have a harder time understanding logistic regression later in the classification videos, and an even harder time understanding more advanced algorithms like neural networks. I hope you enjoyed watching and learning through these videos, and I wish you a great rest of your day.